Today we are discussing about the topic waves of second year portion of intermediate, which is also useful for the CBSE 12th students. So here I am going to discuss the very short answer questions of waves. The very first question is, what does a wave represent? So when we talk about waves, a wave is the movement of a disturbance in a medium without the actual movement of the particles of the medium. So in this process, the wave transports energy in the medium. So the very first answer is this. The next question. Distinguish between transverse and longitudinal waves. When we classify waves, they are mainly of two types. The main classification is the progressive waves and the stationary waves. And in the progressive waves, we have again two types, that is the transverse and the longitudinal waves. So when we talk about the transverse wave, the second one A bit, I am just representing it diagrammatically. So when we talk about a transverse wave, the definition goes as follows. A wave in which the vibrations of the particles of the medium are perpendicular to the direction of the propagation of the wave is called as a transverse wave. For example, let us take a string which is hooked to a fixed wall. Now if I move the string up and down, then a wave or disturbance is caused in the string. So here the particles are moving, they are vibrating up and down, but the wave is propagating perpendicular to the direction of the vibrations of the particles. So this is the direction of the wave. Wave is the disturbance. So a transverse wave is one in which the directions of vibrations of the particles are perpendicular to the direction of the wave propagation. So this transverse wave actually takes place mostly in solids and not in liquids. The reason being, because liquids, we do not have the shearing stress or the shearing strain. That is the reason mostly transverse waves are produced in solids or surface of liquids. Another type of waves are there. For example, they are the electromagnetic waves. So in electromagnetic waves, light waves which do not require a medium for their propagation, but they are because of the oscillating electric and magnetic fields which these waves are generated. So light waves also can be taken as an example of transverse waves. So these transverse waves are produced in solids or surface of liquids, but mostly in solids. Then next let us go to the B part, that is the longitudinal waves. A longitudinal wave is one in which the direction of vibrations of the particles are parallel, that is in the direction of the propagation of the wave. So that is, we will just take some few examples. For example, suppose I compress a spring, it is a spring and I just compress it. I am just compressing it. It moves up and down. The spring vibrates up and down, and the wave also is going parallel to the direction of vibration of the particles. So this is one of the examples of longitudinal wave where the direction of vibrations of the particles is parallel to the direction of the wave propagation. But one thing we must remember is the medium itself is not moving away. The particles are not moving away. They are executing SHM about their positions, but what is moving is the disturbance, which we call it as the wave. And this disturbance transports energy. Hence, wave is one which transports energy. Another example for this is, suppose you have a cylinder which contains a gas and then you are compressing it with the piston. So, the air particles, when you compress it, they come very close, and again when you just release the piston, they move apart. So, at this time also the particles are coming close and also moving away, but the directions of vibrations of the particles are parallel to the direction of the wave propagation. So, hence these two can be considered as the examples of longitudinal waves. But now that we are discussing about sound, sound is a longitudinal mechanical wave in a gas. Why am I specifying in a gas? Because when I tell mechanical wave, a wave which requires a medium for its propagation. That is, the medium can be a solid, a liquid or a gas. So, when I talk that sound is a longitudinal wave, it happens in gases or air, it is longitudinal. That is, the air particles are vibrating parallel to the direction of the wave propagation. For example, when I am speaking, so as I am speaking, different people are able to hear me in different directions. That is because there is air everywhere. So, the particles adjacent to my mouth first vibrate, they execute SHM, they convey the SHM to the adjacent particle, that in turn conveys the disturbance to the adjacent particle. So, that way a disturbance is being propagated without the particles moving away. So, hence a longitudinal wave, the particles vibrate parallel to the direction of the propagation of the wave. But when you write the answer, you have to just write the definitions of both of them and give examples, any one example and where are they produced. So, here you can give any one of the examples and you can tell that this longitudinal waves are produced in solids, liquids as well as gases. So, this is about the second question. So, now let us go to the third question. What are the parameters used to describe a progressive harmonic wave? So, whenever we talk about the parameters used to describe a progressive harmonic wave, we talk about the displacement equation of a progressive harmonic wave. What is a progressive wave? A wave which originates at a point in a medium and moves into an infinite space without getting reflected back at any point is called as a progressive wave. So, such a progressive wave, when we talk about the displacement equation, it is represented by y is equal to a sine omega t plus or minus kx plus or minus phi. So, here y represents displacement. So, this is one of the parameters where the wave displaces by some amount. A, the maximum displacement of a particle from its mean position is called the amplitude. So, A is the amplitude of the wave. Omega. Omega is called as the angular frequency, also called as angular velocity or angular frequency, and we know that omega is equal to 2 pi n. In some books they represent the frequency as small letter. This is called linear frequency, this is called angular frequency. Linear frequency is denoted by small letter f or n. So, omega is 2 pi n. So, you can, one of the parameters is also the linear frequency which is n and angular frequency omega. Then we have K. K is called as the wave number, and it's also sometimes referred to as the propagation constant. And K is given by 2 pi by lambda, where lambda is called as the wavelength of the wave. So, lambda is called as the wavelength of the wave. Now, what is wavelength? The distance travelled by a wave for one vibration, or during one vibration, or during one oscillation, or in rotatory motion during one rotation. So, whatever we say, the wavelength is the distance travelled by a wave during the time period capital T. So, another factor which is T is also called as the time period, because when we refer to this omega, it is also given as 2 pi by T. Omega is also equal to 2 pi by T, where the reciprocal of time period is called as the linear frequency of the wave. So, whenever we are asked to write this answer from examination point of view, first you must write the progressive wave equation. After writing the progressive wave equation, this plus and minus sign indicate, for your knowledge, they indicate the wave travelling along the positive x-axis, it is written as minus kx. If it is along the negative x-axis, it is written as plus kx. So, either one of them you can use. So, in general, you must write the entire equation and again describe the terms, but just because omega is there, you must not eliminate about time period and frequency. You must also mention about them, and also we also write another parameter which is called as the linear velocity of the wave, V. V is called the velocity of the wave. Angular velocity and linear velocity. So, all these are the parameters of a progressive wave. Next, let us get back to the fourth answer. Obtain an expression for the wave velocity in terms of these parameters. These parameters means, in the previous question we have seen what are the parameters which we have used to describe the wave, progressive wave. So, now we are obtaining an expression for wave velocity, that is V. I have just now discussed about V. So, wave velocity V in terms of the parameters. So, in general, when you have learnt in school, how do we define velocity? Velocity is the rate of displacement of a body. It is a vector. Yes. So, velocity is displacement by time. It is the rate of displacement of a body. But here, when we talk about velocity, wave velocity, we generally define two terms. The very first one is the time period T. So, you must write the definition of time period T. Yes. So, what is time period T definition? It is the time taken by a particle for one vibration. So, the time taken by a particle for one vibration, for one complete vibration, is called as the time period T. Yes. So, next, when we talk about the frequency, the number of vibrations made by a particle in 1 second, means in 1 second time it can make any number of vibrations. So, that is called as the frequency. So, for example, if I take a particle, its mean position is O. So, it is vibrating about two extreme positions of nearly the same amplitude. So, let me call the extreme positions as A and B. So, the particle at O, it starts at one point, has a maximum displacement which I called it as amplitude A, and it again comes back to this point, goes to the other side, again comes back to O. Then you say one vibration has been made. So, this is the mean position. Similarly, one vibration can also start from the extreme position A. A particle starts at A, goes like this, goes to B, comes back to O, but still it didn't come back. It should come back to its point of origin, its original position of start. So then we say one vibration is completed. So how do we say one vibration? When a particle returns to its point of start, then you say one vibration is completed. So that position of start can be mean position or extreme position, either one of them. So based on which we have different equations. So if the particle starts from O, goes to B, comes back to O, again goes to A, comes back to O, the time taken for one vibration is called as a time period T. But a particle may make so many vibrations like that. So the number of vibrations made in 1 second time, in a time of 1 second, is called as frequency N. Hence, we have a relation between frequency and time period as N is equal to reciprocal of time period. And its SI unit of frequency is Hertz. In small letters, because it's a name of a scientist, we write it as Hertz, symbol way Hz, or vibrations per second, cycles per second. That is and time period, it has a unit of second. Now, in this question, obtain an expression for the wave velocity in terms of these parameters. So when we take velocity, wave velocity V, it is given by displacement by time. So for one vibration, because here we are specifying the word one, for one vibration, what is the displacement? Displacement is lambda. Lambda is nothing but wavelength. So how do we define wavelength? So here main thing you have to define what is time period, what is frequency, what is wavelength. All the three definitions first you have to give. Then give the general definition of velocity, which is displacement by time. So wavelength is nothing but the distance travelled by a wave for one vibration or during the time period T. The distance travelled by a particle during the time period T, the displacement of a particle during the time period T is called as wavelength lambda. So now let us substitute V is equal to, because we are telling for one vibration, lambda, the time taken for one vibration is capital T, and we know that 1 by T is equal to, what is 1 by T equal to? N. So we write V is equal to N lambda. So this is how you write the expression for velocity, or this is the expression for wave velocity. So let's proceed to the next question, which is question number 5. Using dimensional analysis, obtain an expression for the speed of transverse waves in a stretched string. When they talk about dimensional analysis, you would have learnt in units and dimensions how to write the dimensional formula for various parameters or various quantities, physical quantities in physics. So when we talk about the dimensional analysis, basically what does a dimensional formula represent? A dimensional formula represents the unit of that particular quantity. This is all you would have done in detail, but whatever it is, a dimensional formula represents a unit of a particular quantity. So by writing the units in terms of the basic quantities like mass, length, time, we should derive the expression for the speed of transverse waves, because theoretically also you have another method to derive, but here because he is asking using dimensional analysis, you have to derive it only dimensionally. So when we talk about the speed of a transverse wave in stretched strings are solids and the waves produced in them are transverse, because when we pluck a string, the particles are vibrating perpendicular to the direction of propagation of the wave, and hence such a wave is called as a transverse wave. So when I talk about the speed of a wave in stretched string, for example in your musical instrument like veena, you pluck a string. So what are the vibrations caused there? Transverse vibrations, which cause transverse waves. Actually, again they superimpose and form stationary waves, which we will learn later. But right now, the main thing, when I stretch a string, what are the two parameters on which mainly it depends? First thing, the string has a certain mass and it has a length. So we have a term called as mu, which is called as linear density. Usually when we learn density, what is density? Mass by volume. That's how we have learnt in our school. When we talk about linear density, it is mass by length. When I talk about areal density, mass by area. So the same way here it's linear density, because when we take a string, mostly the parameters which we define for a thin string or stretched strings is not in its volume or area. We talk about length. So that's why we discuss about the linear density. So what is linear density? Mu. It's nothing but equal to mass of the string by its length. So mass by length. This is linear density. Its unit is, in SI unit, kilogram per meter. That's how we write the unit for linear density. So what is its dimensional formula for linear density? What is the dimensional formula for linear density will be mass m by length L. So what is the dimensional formula? M L inverse. Means mass has dimensions of 1, length has dimensions inverse L inverse, time is 0 dimensions. So this is the dimensional formula of linear density. Another factor on which the velocity of the string depends is the tension which it is subjected to. So when we talk about the tension in the string, here see, tension is also denoted by T, capital letter T. So tension is a type of force. So the dimensional formula of tension is, for force, what is force? Mass into acceleration. So mass m, acceleration is Lt minus 2. So this is the dimensional formula of tension. So mass has dimensions 1, length, and T minus 2. Here T is time. In dimensional formula, this T denotes time. Okay. So now when we take the velocity of a string, let us tell the velocity of the transverse wave is directly proportional to, because we don't know how to derive the formula. So let us tell it is proportional to A dimensions in tension and B dimensions in linear density. What do I mean by dimensions? Dimensions are the powers to which a quantity, not a fundamental quantity, any quantity, the powers to which a physical quantity are raised is called as the dimensions of that particular quantity. Like for example, suppose if I take the dimensions of time in tension, how much is the dimension? Minus 2. So minus 2 is the power. So this we call as dimensions. But when I talk this whole thing, it's called dimensional formula. So let us say the velocity of the transverse wave is directly proportional to A dimensions of the tension and B dimensions of linear density. So when I remove the proportionality sign, I can introduce a constant, some constant k. So V is equal to k T to the power A mu to the power B. So now let us write the dimensional formula of velocity. What is the dimensional formula of velocity? Lt minus 1. That means it has a dimensions mass 0, L1, T minus 1. So that is the dimensional formula of velocity. So dimensionally, let us substitute the dimensional formulas and see. K, it's a constant. So it has no dimensions. Constants do not have any dimensions. So K has no dimensions. So dimensionally, when I substitute for velocity, it is m0, L1, T minus 1 is equal to constant, no dimensions. For tension, Tension is what? Force, mLT minus 2. So, m1 L1 T minus 2, and dimensional formula of mu is m1 L minus 1 T to the power 0. So, dimensionally equating these equations, let us say when I talk about the dimensionally, when you are equating these equations, what we can say here, V is proportional to T to the power of A. Tension to the power A means what do I get here? M L T minus 2 to the power of A. And mu is what there? Mu is linear density, mass L minus 1 to the power of B. You must write this, A to the power B. So, let us equate the dimensions. What are the dimensions of mass here? We will equate the mass separately. So, this is m to the power A, m to the power B. So, m to the power A plus B. L to the power A minus B. T to the power minus 2A, because here there is no dimensions of time. So, what do we have? Mass mLT minus 2 to the power A, mL minus 1 to the power B. So, A plus B, A minus B. Here it is m to the power 0, L to the power 1, T to the power minus 1. So, equating, we get A plus B is 0. Powers of mass. Then powers of length and powers of time. What is time? Minus 2A is equal to minus 1. See, we don't need to bother about length, because minus 2A is minus 1 means what is A equal to? Half. So, which implies, what does the first formula imply? A is equal to minus B. So, if A is half, what is B? Minus half. So, let us substitute in equation number 1. So, what do we get? V is proportional to T to the power half and mu to the power minus half, or V is equal to some constant square root of T by mu. From experiments, K is equal to 1, which implies that V is equal to root T by mu. So, this is how you derive the expression for the velocity of a transverse wave. Because I have explained, it took long time, but actually how you should present the answer is, let V be again I am repeating it, let the velocity of the wave be proportional to A dimensions of tension and B dimensions of linear density. Write the dimensional formula of tension, linear density, and you equate the powers and equate the powers of mass, length, time, find out the constants A and B, and just write that from experiment K is equal to 1, and hence this is the equation for the velocity of the wave. Next, let us go to the question number 6. Using dimensional analysis, obtain an expression for the speed of sound waves in a medium. So, previously in question number 5, we have discussed the velocity of a transverse wave. Now, we are going to get an expression for the speed of sound waves in a medium. So, sound waves, that is the medium can be solid, a liquid or a gas. Of course, sound waves in air are longitudinal, that we have discussed. Whatever it is, this is the speed of sound waves in a medium, again by dimensional methods. So, when I talk about a sound wave, the main factors on which the speed depends are, like when I am talking, or if I compress a piston, what is varying, which quantity is varying there? The pressure. The pressure and density of the medium vary. So, the factors on which the velocity of a sound wave depends are the pressure P and the density rho. So, same way, just like the previous one, we will tell, let the velocity be proportional to A dimensions of pressure P and B dimensions of density rho. So, here dimensions of velocity V are LT minus 1 velocity pressure. What is pressure? Force by area. Force has a dimensional formula of mLT minus 2 by area is L square. So what do we get? The dimensional formula of pressure, mL minus 1 T minus 2. So this is the dimensional formula of pressure. Density rho. Density, what is the formula? Mass by volume. So what do you get? mL minus 3, because volume L cube. So m by L cube, mL minus 3. So let us just find out how does this work out. So let us say V is equal to again some constant into pressure to the power A, rho to the power B. So this is our equation 1. This is our equation 2. Because you are removing the constant of, you are removing the proportionality sign, I have introduced a constant of proportionality. So let us substitute dimensionally. LT minus 1 is equal to, constant has no dimensions, K has no dimensions means M0, L0, T0. That's how you represent no dimensions. So let us not substitute about that. Pressure. What is pressure there? M L minus 1 T minus 2 to the power of A. And density mL minus 3 to the power of B. So again let us compare the coefficients. So here it's nothing but m to the power 0, L to the power 1. So let us compare the coefficients. So what do you get here? M to the power A plus B, similar to that. Then here what do you get? L to the power minus A minus 3B. Minus B, and then T to the power minus 2A. M to the power 0, L to the power 1, then what do you get? T to the power minus 1. So similarly, see, you need not bother about the dimensions of length here. A plus B, it implies that, I'll rub this out. So it implies that comparing the coefficients of mass, length and time, it implies that A plus B is equal to 0, which implies that A is equal to minus B. From comparing the coefficients or comparing the powers of mass. Now comparing the powers of time, you get minus 1 is equal to minus 2A, which implies that A is equal to half. Thus, B is equal to minus half. So similar to that, substituting in equation 2, what do we get? What did we write the equation 2? K has no dimensions. So K, no dimensions. And from experiment, K is equal to 1 from experiment. Thus, let's get back to equation 2, which I wrote it as V is equal to K. What did I write? V is equal to K, P to the power A, rho to the power B. Pressure, density. So, V is equal to 1. K is 1. Pressure, P to the power A is how much? Half by rho to the power half. Because B is minus half. So, it's nothing but rho to the power half. So, V is equal to root of P by rho. So, this is the expression for the velocity of the sound waves in a medium, which is root P by rho. This is called as Newton's formula. Newton's formula, which was not true exactly. Then Laplace, he was another scientist who made a correction. I just want to mention this point. Your answer is sufficient till here. But Laplace, he was another scientist who made a correction, and actual formula for V is root of gamma P by rho, where gamma is called the ratio of the specific heats of two gases. So this gamma P by rho, this is Laplace correction, but this is called as Newton's formula. And another point I would like to notice here, the Young's modulus when I talk about pressure, P, dimensionally for liquids, it is the bulk modulus, because the bulk modulus is also something variation in pressure. So, just for a knowledge sake. Then, coming to the 7th answer, what is the principle of superposition of waves? When we talk about superposition of waves, it is number of waves or pulses. Pulses means it's a wave only, a disturbance in a medium. So, when a number of waves, they may be moving in the same direction or they may be moving in the opposite direction. But whatever it is, when a number of waves moving in a medium, they superimpose on each other, that is they interfere with each other, then the resultant amplitude will be the sum of the displacements of the individual waves. That is, the resultant amplitude or displacement of the wave will be the sum of the individual displacements of the waves. That is, each wave will have its own displacement, and when we sum up all the individual displacements, then it will be equal to the net displacement of the resultant wave. So, how do we define it? The actual definition is, let me first tell you the mathematical part of it a bit, and then we will go to the definition. You should just write the mathematical equation and the definition, because it's only a 2 marks. So, let us tell the first wave is, say, y1. So, whenever I talk about a progressive wave, how do we write it as in a simple way? A sine omega t plus or minus kx. This is how we write it. So, we can write a wave is actually a function of, that is when I write it as a function, the displacement equation, it is a function of displacement and velocity. Okay, so generally I can write it like this, any wave. Let us just represent the displacement in general terms like this. So, if I tell the first wave is y1 is equal to f1 x minus vt, this is a first wave. The second wave has a displacement, it's a function of f2 x minus vt. Then we write the resultant wave yr is equal to y1 plus y2 plus so on. So, plus yn, that is if we talk about n waves. So, this is nothing but, when I add up all this, I can write it as equal to sigma fi x minus vt. Sigma is a summation, I ranging from 1 to n. So, if I put the first wave f1 x minus vt plus f2 x minus vt plus f3 x minus vt, so on till yn. So, this is the mathematical expression for the principle of superposition of waves. So, whenever you are writing this 2 marks question, first you should write the definition, and then briefly if you write this mathematical expression, this part of it, it is more than enough. So, just the definition and this, you will be getting 2 marks. So, how, let us define properly. The principle of superposition of waves states that the resultant displacement of the resultant wave is equal to the sum of the individual displacements of the individual waves when a number of waves or pulses are superimposed on each other. So, next let us get back to question number 8. Under what conditions will a wave be reflected? So far we have discussed about progressive waves, where I told that a wave starts from an origin and goes into an infinite medium without undergoing reflection. But there are some waves which reflect at some point. Like for example, when I take any musical instrument like a veena or a guitar, we see that there are 2 fixed ends. So here this, when we pluck the string, it just vibrates. So, this fixed ends, a wave, a disturbance is going like that, and then at this point it reflects back. It reflects back. So, this is a wave. Wave is a disturbance. It's not that the particles are going like this. The particles are moving up and down, but the disturbance is going like this. At this point it undergoes reflection. It goes back. So, you get loop formations of this type which will be drawn perfectly like this. So a wave goes like that, and at one point when it undergoes reflection, it comes back. So you will be getting in the form of loops. Loops are formed like this. You have number of loop formations. You can draw any number of loops between the fixed ends. Provided these ends are fixed, you get the loops like this. So wave going in one direction and coming back in another direction. So here we say such wave is a reflected wave, it's reflecting. So this reflection takes place mainly at three conditions. First one, a rigid boundary. Second one, a free boundary. Free end or free boundary. Then C, at the interface between two media. So he asked us here, under what conditions will a wave be reflected? So first one, at a rigid boundary, at a free end, or at the interface between two media. So these are the conditions where a wave will be reflected. But just if you write these three answers, it's more than enough. So here, just for explanation, suppose we take a closed pipe. This will be a rigid boundary, or the fixed end for a string. Free end. What is a free end? Suppose you have an open pipe which is open at both the ends. Like a flute, when we blow air into a flute, vibrations are caused. But the medium abruptly ends here. So such an end is called as a free end or an open end. Then at the interface between two media. So suppose there are two different media like water and air. There are two different media. So at the interface, at the juncture of the two, the wave can be reflected. So you have to write a rigid boundary, free end, and the interface between two media. So let's go to question number 9. What is the phase difference between the incident and reflected waves when a reflected wave, that is when the wave is reflected by a rigid boundary? Rigid boundary, just now I have explained to you. So what we are saying, there is an entire phase reversal. That is, for this we can just write the phase difference between the incident and reflected waves when the wave is reflected by a rigid boundary is pi radians. Or 180 degrees. Why do we say this? That is, what do we mean by a phase change of pi? Phase change of in phase and out of phase. These are two things. This is for explanation. You can write the answer like this. So when there is out of phase, just now we have told a wave is going in one direction and suddenly it gets reversed. Means when we calculate the phase angle between the two, it turns out to be 180 degrees. So here the wave is reversed its direction. So this phase difference is 180 degrees. That is, in terms of angle, actually you can calculate, but if for this answer you can just write it, it's pi radians of 180 degrees. That is, they are out of phase. Yeah. Next question. What is a stationary or standing wave? So he's just asking the definition here. So when we talk about stationary or standing wave, I told you the main classification is progressive wave and stationary waves. Progressive waves are transverse and longitudinal waves. So stationary waves also can be due to transverse or longitudinal waves, but when they superimpose on each other. So the best example is musical instruments or stretched strings, where you have two fixed ends and the strings are in between them. So when we pluck a string in the middle, exactly in the middle, these are the two ends. These are the fixed ends. So when I pluck a string, let us tell the least type of vibration is one loop. Or if I just talk about a wave, just like the previous example, when I pluck it somewhere, I vibrate it. A wave is going in one direction and it reflects back. So it's going in this direction. See, let us tell this wave is going like this. It's going like that. At this fixed end, it suffers reflection, a phase change of pi, and it is coming back like this. So actually, there are two progressive waves provided they have the same amplitude. That means, if this is plus A, this should be minus A. Means usually amplitude and displacement are vectors. So the negative sign does not indicate value. It only indicates opposite direction. Whenever we take vectors, like for example in scalars, when I tell 5 and minus 5, value changes. Minus 5 is less on a number line. But in vectors, it's not like that. In vectors, when I tell a displacement of 5 meters, displacement magnitude is 5 meters. This negative sign only indicates displacement in the opposite direction, but its magnitude is 5 itself. So the same way, here the two waves. So when two progressive waves of same amplitude, time period, velocity and wavelength moving in opposite direction, the word opposite is very important. Moving in opposite directions, superimpose on each other, then the resultant wave is called as a stationary or standing wave. So in such a process, what happens is, when suppose the maximum of one wave falls on maximum of another wave, the resultant wave has a maximum amplitude. That is, if this is A and this is A, the resultant wave has a maximum amplitude of 2A. But that is, if the suppose if I take a transverse wave, a crest of one wave falls on a crest of another wave, the resultant wave has a maximum amplitude. But if the crest falls on a trough of another wave, then the resultant wave has minimum amplitude because they are superimposing on each other. So at such points we say antinodes are formed. Actually there is a mathematical thing, but because this is a 2 marks question, this is only for your knowledge. But you need to write only the definition and just draw the diagram. And these are called nodes. So these points with 0 amplitude are called as nodes, N. That is, the net amplitude of the resultant wave is 0 because the crest of one wave would have fallen on the trough of the other wave. The positions where the amplitudes are maximum are called as antinodes. So the position of the resultant wave, that is the resultant wave, the positions where the resultant wave due to superimposition has maximum amplitude is called as antinodes. So such a wave is called as a stationary wave. What do you understand by the term node and antinode? See, just now in the definition I have mentioned, there also you should mention, because when you write the definition you have to draw the diagram and just mark the points as nodes and antinodes and just briefly explain, because it's a 2 marks question. Here we will write separately the definition of a node 1 mark, antinode 1 mark. So let us write the answer for 11th question. Node, it's represented by N. Nodes are positions or points in a stationary wave where the net amplitude or displacement of the resultant wave is 0. So that's enough. That is the definition of a node. Now let's go to the definition of antinode. See, this is only a representation. You can represent anything, but you have to mention, because amplitude also we represent by A. But here we are referring to antinode A. So antinodes are the positions or points in a stationary wave which represent the maximum amplitude of the resultant wave. The next question, what is the distance between a node and an antinode in a stationary wave? So whenever we talk about a wave, now let me first give you a small explanation and the answer part of it I'll tell you later. First, just some brief knowledge about it. So when we talk about a wave, I told you a wave is represented actually by a sine curve. So one wave, suppose we say this is the time period t, that is time taken for one vibration. So one vibration is represented by one wave. This we call it as plus amplitude, this we call it as minus amplitude. Suppose another wave, it goes on, dot dot dot, it continues. So here this will be exactly, this point will be exactly half the time period. The distance travelled by the wave during time period t is called lambda, the wavelength. Fine. So how did we get this time period t actually? This is a displacement time graph. What are we plotting is displacement time graph. For example, if I take a simple pendulum, this is the mean position. For small vibrations means this is less than about 6 degrees, then only it will go straight. If I put it more, it goes oscillatory motion, then it is not SHM. Only for very small angular amplitudes 6 degrees, we say it's an SHM. So let me call this as C and B. These are the extreme positions. So suppose I tell this is the mean position 0. That is at a time t is equal to 0, displacement is what? 0. But as the time is increasing, displacement is increasing. So as time is increasing, displacement is increasing. It becomes maximum. Plus A. In one direction, displacement is positive. So when it comes to position B, displacement is maximum and I call this as plus A. So it comes to plus A. After it comes here, again what's happening to the displacement? It's gradually decreasing. So in the graph, it's gradually decreasing. Then half the time is over because see I told you time taken for one oscillation is t. So from O to B and B to O, how much is the time? T by 2, half the time period. So it came back to displacement 0 position, the mean position. Then it goes to the other side. I told you displacement is a vector. So in the other side displacement is negative. So again what's happening? Displacement is increasing in the other direction. So it is increasing. So it's increasing. I represented it by minus A because it shows opposite direction. Then again it comes to maximum displacement C, where I called it, this is C. This is the position B. This is O. Okay. So at C the displacement is maximum. This is minus A. Again when it comes to C, the vibration is not completed. It has to come back to O. So again from maximum displacement it is decreasing. Displacement is decreasing and it comes back to O. So one vibration is done. So time taken is capital T. Half the time it is T by 2. So one wave is represented by one of the sine curves. So here what we say, a node and an antinode. So in stationary waves, when we say this is a node, this is a node, this is a node, this is an antinode, this is an antinode. Because this is maximum displacement, these are positions of minimum displacement. So one wave, what is the time period? T. Half the wave, time period T by 2. The wavelength here is lambda. Here what is the wavelength? Lambda by 2. So half of it, this will be lambda by 4 wavelength. Time period will be T by 4. So in this question, see actually what is the distance between a node and an adjacent antinode? That correction should be made in the adjacent antinode in a stationary wave. So node and adjacent antinode, the wavelength is lambda by 4. This is the answer. If they tell alternate, then it will be lambda by 2. See, between two nodes it's lambda by 2 and plus lambda by 4. So, like that you have to calculate. So, between node and adjacent antinode, the answer is lambda by 4. What do you understand by natural frequency or normal mode of vibration? So, whenever we take any body, it has its own natural frequency. What do we mean by its own natural frequency? That is, if I vibrate any body, depending upon its dimensions and its elastic nature, it vibrates with it makes a certain number of vibrations per second. So, that is called as a natural frequency, but we can't define it this way. There is a definition for it. So, when we say the frequency with which a body vibrates on its own, which depends on its dimensions, the elastic constants and the mode of vibration, is called as the natural frequency. So, this is how we define the natural frequency of a body. So, the factors on which the natural frequency of any body depends are the mode of vibration, its elastic constants and its dimensions. 3 factors on which they depend. Natural frequency is the frequency with which a body vibrates on its own when it is made to vibrate by an external agency. What are harmonics? So, when we talk about harmonics, we say that, like for example, we have seen in stationary waves. Suppose if the string is plucked at the center, it vibrates in one loop. If the mode of vibration is changed, it may vibrate in 2 loops or it may vibrate in 3 loops. So, it goes on. So, here harmonics, here he is asking us just the definition of harmonics. Harmonics are the higher frequencies of vibration which are an integral multiple of the fundamental frequency. Harmonics are the higher modes of vibration which are an integral multiple of the fundamental frequency. For example, suppose if I tell the fundamental frequency of a body is say n, then the harmonics can be like 2n, 3n, 4n, p times n. So, these are called the higher modes, higher frequencies where it vibrates. So, this vary from each example. For example, in strings it is different, in closed pipes it is different, in open pipes they are different. The definition is the higher order multiples or higher order frequencies which are integral multiples of the fundamental frequency are called harmonics. Then we have, because at this point I just want to distinguish between a harmonic and an overtone. Overtone are also higher order frequencies, but they may or may not be an integral multiple of fundamental frequencies. Like we can have 1.5 n or 2.5 n. So, this 0.5 overtones can also be 2n. So, they may or may not be integral multiple. But harmonics are always an integral multiple. They are higher order frequencies which are an integral multiple of the fundamental frequency. A string is stretched between 2 rigid supports. What frequencies of vibration are possible in such a string? See children, this is just a 2 marks question. So, you should not elaborate more on this. So, what frequencies of vibrations are possible in such a string? So, you have to just tell. Just draw that and again draw stationary waves depending upon how many ever loops you can form. The fundamental being one loop. So, they can go anywhere between 1 to 2, 3, 4, any number. So, what are basically formed as stationary waves. So, how do we say the frequencies of vibration possible in such a string? So, in a stretched string, for one loop, like suppose it is a 4 marks question, you have to derive. But here we say stationary waves are formed with number of loops and the frequencies are given by P is the number into, like we write this as V by 2L. So, here P is equal to 1, 2, 3, 4, so on. V is the velocity of the transverse wave. That is equal to root of, previously we discussed tension by linear density. So that is a formula for velocity of the transverse wave. And here we say N naught is the fundamental frequency. Of the string, and that is nothing but equal to when we tell that P is equal to 1. That is, when the string vibrates in one loop, it's called as a fundamental frequency, and we have the frequency as V by 2L. If it vibrates in 2 loops, we'll have 2V by 2L. If it vibrates in 3 loops, 3V by. So it has both the even and the odd harmonics. So this is a string is stretched. What frequencies of vibration? So these are the frequencies of vibration which are possible, where it has an integral number of frequencies. Integral means both even and odd harmonics are present. Similarly, 16th question is for a closed pipe. The air column is a long tube closed at one end and is set into vibration. What harmonics are possible in the vibrating air column? This is similar to the previous one, that is for vibrating strings. This is for a closed pipe. So when I take a closed pipe, so this is a fixed end. So there may be water also, but here I am just taking this as a fixed end. So here we have air. So if I take a tuning fork, vibrate it and place its prongs in such a way so that the vibrations are transferred to the air columns. So we see that the air vibrates longitudinally and loops are formed. Because this is a fixed end, it's a rigid boundary, this is a free end. So usually at a free end, antinodes are formed, and at a fixed end you have a node. So suppose if I take the simplest mode of vibration, this is the simplest, that is, a wave is coming like that and getting reflected like this. This is a pipe. This is the simplest mode, a node and an antinode. Suppose next mode we'll have a loop, one loop. All this is not necessary for 2 marks, but just you can just draw a diagram and leave it. So this is the next mode. Here you have a node, antinode, antinode, node. Fixed ends are always nodes. Free ends are antinodes. Node, again antinode. So here what we see is, let me make this a little more bigger because this is half of it. When we talk about the what are the harmonics possible in vibrating column, the fundamental mode here is, what is the distance between node and antinode? I just now told you is lambda by 4. So the wavelength is lambda by 4. Here how much is it? Lambda by 4 plus lambda by 2. So it will come out to be 3 lambda by 4. Lambda by 4 plus lambda by 2. So that is 3. Lambda by 2 is like 2 lambda by 4. So it's 3 lambda by 4. So when we see here, the fundamental frequency is given as, here also, V by 4L, velocity by 4 length. This will derive, but here because it's a 2 marks question, you should just write it. So the first harmonic is 3V by 4L. The next one will be 5V by 4L. So in general, we write the frequencies of vibrations will be 2P plus 1 into V by 4L, where L is the length of the vibrating air column and V is the velocity of the wave. So for this answer, what you are supposed to write is, in a closed pipe, the fundamental frequency is V by 4L and the higher order frequencies are N equal to 2P plus 1 V by 4L, where P ranges from 1, 2, 3, 4, etc. So when I put P also as 0, you get V by 4L, that is N naught, the fundamental frequency. When P is 1, you get 2 plus 1, 3. And when P is 2, how much you get? 5. 2 into 2, 4 plus 1, 5. Next will be 7. So what are the ratios of the frequencies here? N naught is to N1 is to N3, 2 is to N3. How much are they? 1 is to 3 is to 5 is to 7, so on. In general, 2p plus 1. So here there are odd harmonics present. In closed pipes we have odd. So if you write this much, it's enough, and you should just explain a bit. Next question is the 17th one. Same, similar to this. That was a closed pipe. This is an open pipe. So let me read out the question. If the air column in a tube open at both ends is set into vibration, what harmonics are possible? So this is nothing but an open pipe. Open pipe is just like a flute which is open at both ends. So what are form? The basic form is you should have an antinode at open end. So between, you can't have two antinodes, so you should have a node in middle. So basic form of vibration is this, with a node, antinode, antinode. So basically how much do you get? Suppose L is the length of the air column. In this case, how much do you get L equal to? Between antinode and node, lambda by 4 plus lambda by 4. This is the basic fundamental mode. Fundamental mode, length will be lambda by 2. So what will lambda be? 2L. So what is the velocity here? What is the frequency here? V is equal to N lambda. So V is equal to N equal to V by 2L. So this is N naught. This is the fundamental mode. So the fundamental frequency will be V by 2L, where V is the velocity and L is the length of the vibrating air column. So when we talk about the higher order frequencies, you will have one loop in between or two loops in between. So in this case, we write that N, in general, the formula for N will be P into V by 2L, where P will be 1, 2, 3, 4, so on. So here you have both the even as well as the odd integral multiple. So it's just an integral multiple of the fundamental frequency. So when we have P equal to 1, you have the fundamental frequency. For higher orders, N1, you have 2V by 2L, 3V by 2L. So all vibrations are set. So the main thing here is, if the tube is open at both the ends, the higher order frequencies are an integral multiple of V by 2L, where V is the velocity of the wave and L is the length of the vibrating air column. What are beats? So usually when we talk about a beat, we are reminded of a heartbeat. So when we tell about a heartbeat, it's just a lub-dub sound which we hear. We can feel it like a beat. That is a sound of maximum note and a sound of minimum note. A sound of maximum intensity, which is called waxing, a sound of minimum intensity, which is called waning. So when they ask us the definition, actually it is the formation of beats, the phenomena of beats. It's similar to superimposition of waves, but in stationary waves, we have seen that the two waves have the same frequency, but they are moving in opposite direction. But in beats, the two waves will have slight difference in frequencies and they move in the same direction. That is the basic difference between stationary waves and beats. So what is the difference? They may be of same amplitude or different amplitudes, but we usually consider same amplitude. So when two progressive waves of same amplitude with slightly difference in frequencies are moving in the same direction and superimpose on each other, a sound note of maximum intensity and a sound note of minimum intensity are produced at regular intervals or periodic intervals of time. This phenomena is called as beats. One maxima together with a minima is called as a beat. So how do we draw this? So you have to give the definition and just draw the diagram. So let us tell one wave and another wave of slightly different frequency. It should not be more than 10. slightly. So, this is the first wave, this is the second wave. They are moving in the same direction. But suppose if I tell N1, this is N2, N1 difference N2 should be less than 10, means that there should be a small difference but not more than 10. Then you see that the resultant wave that is, even when waves are moving in the same direction, a crest of a wave may fall on a trough of a wave and a sound note of minimum intensity is heard. And when the crests fall on a crest or a trough falls on a trough or a compression falls on a compression, here because it is beats, it's a sound, we usually refer to, means that crest and trough we can refer to stationary waves, in stationary waves also, because they can be compressions, rarefactions or crests and troughs. In beats, mostly we refer to sound waves. So, sound is propagated in the form of longitudinal waves in air. So, we usually talk about compression falling on a compression where you have a maximum amplitude, or a rarefaction falling on a rarefaction maximum amplitude. So, then we hear a sound note of maximum intensity, and that is called as waxing, where you have maximum amplitude. When a compression falls on a rarefaction, then you have a feeble sound which is called waning of sound. So, here the resultant amplitude is almost 0. So, when you hear a loud sound, suddenly a low sound, a loud sound, a low sound, you hear it in the form of a beats. One maxima together with a minima constitutes a beat. The 19th question is, write down an expression for beat frequency and explain the terms therein. So, what is beat frequency? It's not, beat frequency means the number of beats heard in 1 second. So, for example, when I take a wave of frequency, say 256 hertz, and another wave of frequency 258 hertz. What do you mean by hertz? Number of vibrations made in 1 second. So, when I tell frequency, number of vibrations made in 1 second. Beat frequency means number of beats heard in 1 second. So, when I talk about the first wave and the second wave, the formula for the beat frequency is given as number of beats in 1 second, that is heard per second. So, this is nothing but equal to the difference in frequencies of the two waves, because anything can be more. The N1 may be greater than N2 or N2 may be greater than N1. In this case, N2 is greater than N1. So, the difference in frequency here is 2 hertz. That means difference in frequency is this between the waves. N1 difference here, N2 minus N1 is equal to 2 hertz. So, beat frequency will be 2 beats per second. It's not just 2 beats, it's 2 beats per second. That's why we are calling it as beat frequency, which is numerically equal to the difference in frequencies of the two waves. 20th question. What is Doppler effect? Give an example. Actually, this effect was first found by Doppler in light, where when the speed of the source, like when the speed of an engine or the source of light, you see a variation in color depending upon the speed of the objects. The same effect was also discussed in sound, and it was seen that due to the relative motion between a source of sound and the observer, we observe a change in frequency. It's not that the actual frequency is changed, but we observe a change in the frequency. So, we call it as an apparent change. Apparent means what? It's not real. It is just an observed change. So, what is Doppler effect? A common example is whenever a whistling train is approaching a railway station, we suddenly feel that the pitch means here it's the frequency. Pitch refers to frequency. Frequency means the shrillness of the sound. So, when we tell the pitch is different from amplitude. So, usually when we talk about sound, we characterize by three parts. One is the pitch, which refers to the frequency. The other one is loudness. Loudness is amplitude. Amplitude refers to loudness. And quality of sound. Quality of sound. See, these are all just the extra thing. You need not write in this answer, but with this knowledge you can get a better effect. So, that's what I am just explaining this. This is all you should not write in the answer. Quality of sound, which is called as timbre. So, whenever we discuss about sound, these are the three factors which we refer to. For example, when we say a lion roars, it is very loud. The loudness, amplitude is more, but its frequency is not more. It's not shrill, it's loud. But when we tell a mosquito, it's a small mosquito. It makes very small sound. The loudness is less, but its pitch is very irritating. The shrillness is very irritating. So, that refers to frequency, means it makes more number of vibrations per second. So, usually they say ladies have a shriller voice than men. They are louder, but ladies are shrill. Means they have more pitch, more frequency. But men are louder. Their amplitude of the voice is more. Again, that is related to the length of the vocal cords. All that is different. Then quality of sound. Suppose the same music is being played. It is played on a sitar. It is played on a piano. So, the same music is played with same frequency, same loudness. But still you are able to distinguish between one instrument, that this is a sitar, this is a piano. So, that is quality of sound called timbre. So, when we talk about here, what is Doppler effect? Give an example. For example, when a train is coming to a station, we feel that the shrillness has suddenly increased of the whistle. And when it is leaving, the whistling train is leaving a station, we feel that the frequency is decreasing, the shrillness is decreasing. So, we only feel that the frequency is changing. So, this is called as an apparent or observed change in frequency. So, Doppler effect definition, how do we say? The apparent change in frequency due to the relative motion between the source of sound and observer. Observer here means the listener, is called as Doppler effect. Example, the whistling train. The frequency of a whistling train while approaching a listener increases, and when it's leaving, it decreases. So, that is an example. Yes, and where is it applicable? This Doppler effect has many uses. So, those also you can write some of the uses, like it is used to detect some the velocities with which the bodies move. It is used to detect the velocities of the different objects. This is the last very short answer question. Write down an expression for the observed frequency when both source and observer are moving relative to each other in the same direction. So, actually we derive a general expression due to the relative motion between a source and an observer in Doppler effect. And we discuss different cases, both going in opposite direction, same direction. So, the observer is at rest, source is moving away or towards. So, this is a special case where the source of sound, the observer, both are moving in the same direction. So, suppose if I tell apparent frequency as n dash and the original frequency, always the original frequency does not change. Apparent frequency is only what we feel, what we observe, but original frequency of the train engine doesn't change, it remains the same, but the observer feels that it is increasing and decreasing. That's what is apparent frequency and original frequency. So, suppose if n naught is the original frequency, n dash is equal to v is the velocity of sound plus or minus V naught by plus or minus Vs. This is general formula I am writing down, children, first. Plus if there is a wind velocity, that is if the medium is also moving, we consider the wind velocity. This is the general expression for the apparent frequency in terms of the original frequency. Here V is the velocity of sound, Vs is the velocity of source of sound, V naught is the velocity of observer. Here they told same direction and both are moving relative to each other. Then you can just write, if velocity of wind is taken as 0, then the expression is n equal to n dash V plus V naught by V plus Vs. Or you can write both minus sign also. So this expression is what you are supposed to write. So first write down the general expression, but whenever you write the expressions, you must write what are the terms. So you should not just leave it like that. N dash is apparent frequency. N naught is original frequency. V is velocity of sound. V is velocity of sound in air. Suppose if it's in air, it's about 332 meters per second or 330. V naught is the velocity of the observer or listener, because we are listening. Anything you can tell. Then Vs is velocity of the source of sound. Means suppose if a car is producing a horn, car is sounding a horn, the car is the source which produces the sound. And suppose a person is listening, he is the observer who is hearing. And the observer may be standing, then V naught is 0. If the observer is moving with certain velocity and listening to the car's horn, then it is like both they have certain velocities. So this is the velocity of source of what? Of sound. So this can be like a factory sounding a horn, siren, factory sounding a siren, or a car blowing a horn. So in that process the car can be rest and it can be blowing a horn, then Vs is 0. If the car is moving with certain velocity and sounding a horn, Vs is there. Same way. So this is what you should write. So this completes the VSAQs of the chapter waves.